Okay, so I want to kind of continue where we left off. So we're talking about section 10.4 in this projective geometry book by Coxeter. And it was the section on involutions in the finite projective plane. The 2 for plane, and there's 6 points on every line. That's what the 5 means. 5 plus 1 point on every line. And we got stuck on this section. So we counted that there was 120 projectivities on 6 points. And 25 of them are involutions. 15 of them were hyperbolic. And we got a bit stuck on why 10 of them were elliptic. Okay. And so I think now I understand why. Okay. And I understood it basically right after the stream finished. So it was kind of nice. And I think we basically got it right at the end, but didn't quite phrase it properly. So the main thing was that, so the 15, so what it means to be hyperbolic, it just means fixing 2 points. Okay, so if you have 2 points fixed in an involution, we know that's the same as having a harmonic set. Okay, so basically the fact that any 2 points can be fixed in an involution is just equivalent to saying any 2 points can be the 2 diagonal points of the harmonic set. And so basically we just need to pick, and then there's 15 ways to pick 2 things from six things. Okay, so 6 choose 2 is 15. So if we just pick the 2 things that are fixed, we should get all the hyperbolic involutions. And what that's saying is, once you know what 2 things are fixed, then the rest of the involution is determined as well. Okay, so out of the 6 points, once you pick 2 to be fixed, the other 4, okay, so normally they could be switched around in 3 different ways, but because an involution is a harmonic set, the way it switches around has to make it so that the pairs form a harmonic set with the 2 fixed points. Okay, so what that means is out of the 3 possible ways you can pair up the 4 things, okay, only one of them is valid, and 2 of them are not valid. Okay, so that's what we were saying here. So we had this example here where, 18 and 12, if they were fixed, okay, then what has to happen is that 3 has to go to 8 and 0 has to go to 1. Okay, so in particular, if you have an involution 3 goes to 8 and 0 goes to 1, that determines the whole involution, and it forces the other 2 points to be actually fixed because they are fixed in that one. And so therefore they can't be swapped. Okay, so this gives us a way to count the kinds of involutions there are where there's no fixed points. Okay, so because every involution with 2 fixed points, every involution with 2 fixed points is determined by those 2 fixed points. That's why we have 15 of them. Okay, now for the ones which don't have 2 fixed points, they can't have 3 fixed points, unless they're the identity. So we don't have to worry about that. Or they have, so maybe this is like non-identity involution. And we also know that there can't be any that just fix 1 point. You either fix 2, none, or it's the identity. Okay, so if you want to fix none, So what did we do? So if you just wanted to count involutions on 6 points, okay, then you're basically trying to put 6 points in these pairs, okay? And the number of ways of doing that is 15, okay? So we did that yesterday. Now, the question we got stuck on was, well, if we had a pair where it was fixed, then we know that this involution where nothing's fixed is no longer allowed, okay? And it's not allowed because once you have these two, then we know that 12 and 18 are fixed. Okay. But another interesting thing you could do is you could swap the way that these two are paired. So instead of pairing 0 and 1, you can pair 0 and 3, and 1 and 8, for example. It's the same 4 things, but paired differently in 2 different ways, okay? So if you do that, the last two in the pair can only be 12 and 18, okay? So we're assuming we're dealing with a line with P1, P0, P1, P3, P8, P12, P18. Okay, so 12 and 18 are the only other points, so they have to pair together, right? And they can't be fixed, okay? They can't be fixed points because if they were fixed points, it has to be the first one. So we know these two are not fixed. So these two have to have P12 and P18 swapped, okay? So that's where we got stuck. And I guess we got stuck because, well, look at this, okay? So if there's 15 of these involutions, so one for every pair of fixed points, and every time you have one, you can generate these other two that don't have fixed points, then it seems like you should get 30 elliptic involutions instead of 10, okay? 30 being because there's 15 of them, and there's 15 of these, and there's 2 of these for each one of those, okay? Now, okay, so there's, looks like there's 30 instead of 10, but, okay, so the problem is, so what is actually the problem, okay? So the problem is, when you do this kind of pairing, you kind of distinguished, so you've made these 2 points special, okay? And then you've made these 4 points another thing, okay? But once you break that up into these, okay, this loses its distinguished position. So basically what I'm saying is, if, for example, you had P0, P1 over here, well, not P0, P1, but like say P0, P3 over here, right? In its distinguished position. And then you ended up with P1, P8, and P12, P18 over here, right? Then you would have counted that twice, right? So there's something sort of special about that place out of the 3 places that it could be, okay? When in fact there isn't, because in the end you're going to remove that. So I think this is a good justification for why you might divide by 3, okay? To avoid all this, I guess, triple counting things 3 times. Yeah. So you would count this once where P0 and P3 are on the outside, And you count this again when P1, P8 are on the outside. All right, so you count every one of these 3 times instead of 1 time. So that's why in the end it should be divided by 3. Okay, and then the answer becomes 10. I guess if you looked at it another way, you could be subtracting these things from those things. And it looks like you're subtracting, there's 15 of them, right? But that's the problem, because if you subtract 15 from 15, you have nothing left. Okay? But again, the thing you're actually subtracting has them split into 3 different pairs. Okay? So if they're split into 3 different pairs, then the ones with P0 and P1 at the front is going to be the same as the one with P3 and P8 at the front, and these in another order. So we've counted them 3 times, okay? So then you should divide by 3, so 15 then becomes 5, okay? And then when you subtract 5 from 15, then you get 10, okay? That all works out rather nicely, okay? And you basically know that there's the same number of, see, the projectivities, we kind of know a lot about them. So we know that, you know, the projectivities are generated by involution. So any projectivity is a product of 2 involutions. And actually, any projectivity with a fixed point is basically an involution if you compose it with a particular involution that swaps the pairs. Okay, so the involutions, so the parabolic and up projectivities, there should be like around 25 of them as well. Okay, so this leaves you with at least you know, at least 50, there's 120 projectivities altogether. So it leaves you with a ton of elliptic projectivities as well, okay, which was an exercise whether they existed or not. Okay. And so I guess one of the difficulties with figuring out when there's no fixed points is because just taking 3 points to 3 different points doesn't mean there's no fixed points, right? It just means those 3 points aren't fixed. There could be other fixed points. Okay. But knowing that like there's some point that's not fixed, you know there can be at most 2 fixed points because 3 points would fix everything. Okay, so I think this completes our discussion of 10.4. Okay, and it's a good sort of summary for chapter 5 as well. So when we do 10.5, you might want to review some chapter 6 stuff. So in particular, there's this basic fact about 2-dimensional projectivities. Is that they're determined by 4 points or 4 lines. Okay, so whereas projectivity in 1 dimension is determined by 3 things, in 2 dimensions determined by 4 things. Okay, so that was 10.4. The next thing I want to complete, is it also 12.4? 12.4 or 12.5? All right, 12.4. Okay, so let's continue to 12.4, and it's kind of amazing. I mean, so we got a fair bit through it, and at some point I was really tired, and all this stuff kind of looked pretty hard when we got tired. And then now that when you're not tired, it actually all looks pretty reasonable again. So your mental state is actually a big factor um in all of this. Okay. So let me just remind you where we're up to. Okay. So we're up to this. So we're doing some coordinate transformation to define a collineation. And the way we do it is essentially to use barycentric coordinates about P, Q, and R. Okay, so we've got homogeneous coordinates, which is essentially barycentric coordinates for 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, and so basically, we have some transformations that takes x1 prime, x2 prime, 3 prime. Maybe I could write this as a column now, so it save me some space. And then this was p1 x1 plus q is p. I think it's p1, p2, p2 x2 plus p3 x3, and so on. q1 x1 plus q2 x2 plus q3 x3. And then it's R1 x1 plus R2 x2 plus R3 x3. Okay. Yeah. So this transformation we verified was a point-to-point transformation that preserved incidence. Okay. And what it is basically you can view it in two ways. You can view it as having a point expressed basically in barycentric coordinates with respect to this triangle or with respect to this triangle. Okay. So if the original x's were expressed with that triangle, then the new x, the image will be something that expresses that original point with respect to the new triangle. Okay. Yeah. Or you could think of it as so there's one way to think of it. It's really relabeling them with respect to different triangle, or actually moving the point somewhere else if you keep referring it to the same triangle. Okay. Basically, the reason it preserves incidence, we'd already covered this, okay, but it does come back, is because you have this x prime dot p x1 plus x prime dot q x2 plus x prime dot r x3 equals 0. And x prime dot x equals 0. So basically, it preserved incidence because these two statements are equivalent, and then what they are is that they express collinearity. Okay, so so this dot product means that this point lies on this line. Okay, so basically, if there exists a line for which um, how many points is it? So I guess if we want points to lie on a line, so oh, okay, I see. So this should be a prime. Yep. So this is saying um, the image of x lies on some line. Okay, and then this is saying that the original point x lies on some line. So I guess the last thing we did was show that they were equivalent. So what this is, okay, is basically if you expand all this out, you get the two different versions of this. Yeah. So if you expand this out equals 0 and use this to get that, then these three terms should be columns of this. The columns of this thing together with the appropriate big X terms. And we covered that last time, okay? Hmm. Okay, so I'm starting to try to remember what it was about. So this is saying the x prime lies on some line, okay? And what's this saying? It's saying that the original x lied on some. So it's saying the original x lies on the line with equation. So the line x dot p x prime dot q x prime dot r. Okay. Remember, this is like the equation of that line with these coefficients, and so that line on that line is like you sub those points in, and it's equal to 0. So when little x lies on this line, then the image lies on the x prime line. Okay. So maybe this is also a motivation for how to define the images of the lines, right? So actually, the images of the x's are just the dot products with P, Q, and R. So it's the same definition for the line. Okay, so if you have two definitions, one for lines and one for points, then preserving incidence is just preserving this relationship. And so this equation here is exactly saying that this dotted with x is equal to 0. Okay. And that's probably a more symmetric view, as opposed to having just points and then showing that 3 points are collinear. 3 points lie on the same line. Yeah, that also works too, right? If 3 points lie on the same line, then you just vary these little x's, and this is all going to be 0. And then you have the primes of those x's are going to make this 0. So they still all lie on the same line. Okay? Okay, so actually it was kind of funny. We got stuck at some point here. And looking back on it, I think we actually have pretty good reason to be stuck, okay? So this is one of those points where it's actually probably better to be stuck than to be unstuck without realizing you missed an important point. So we had that. Okay, so we have now a point and a line transformation. So it's a collineation, okay? And the question was, why is it projective? Okay? And it's projective. Well, to check it's projective, okay, so it says in the book from 6.11, it suffices to check that it's projective on one thing, okay? And so that's fine, but there were some other points that were kind of interesting, okay? So we basically had the point 0 mu, which is not just a point, but a whole line of points, right? It's on the line 1, 0, 0. And then we transformed that by this correspondence to basically this set of points. I guess I won't really bother to write what line that lies on. Okay, but the point was, why is that even a projectivity in the first place? Why is there a projectivity that does that? Okay. Well, first of all, so this requires to remind ourselves of what happened in 12.3, okay? So in 12.3, we had that if we had basically 3 points, so we had like, in this case, it'd be 0, 1, 0, 0, 0, 1. So that's the endpoints where mu is 1 and mu is 1. And if we had the sum of those, 0, 1, 1, okay? And then we took any other 3 points, okay? So it took any other 3 points. So in this case, it'd be Q and R, and then Q plus R, okay? And if they were related by an elementary correspondence, or sorry, a perspectivity or a projectivity, okay, then remember when we verified the fundamental theorem, we knew that any other point could be expressed as 0 mu 1, and that projectivity would take it to the same. I'll write mu here. To take it to the point with the same mu, okay? Okay, and that mu was the cross ratio. So The mu was the cross ratio, and it verified that the fourth point was determinant, right? And another way, and then it confirms our way of thinking about it. It had to be the cross has to be the right cross ratio, right? And so in this way, it verified the fundamental theorem. Anytime we had 3, you had the fourth. Okay. And so for us, all we need to show is we can have basically when mu equals 1 and nu equals 1, it goes to q plus r, with the endpoints also going to each other. And then by that verification, the cross ratio forces the other things to be the right proportion. Okay. Okay. But then another issue came up. Okay. Another issue was that basically, actually, so it's more of a temptation than an issue. So if you had basically 2 points, so you connect them up, and you connect them up. See, the thing about homogeneous coordinates is you can kind of rescale things so that the middle thing, so like these 2 points correspond somewhere. The middle thing, you can rescale things so that it's always q plus r, and this is always that plus that, okay? So then you might be tempted to say, well, then it's vacuous because you can always make it like that, and then by that cross ratio thing, the fourth point is always the right amount. Okay. So this is exactly what we can't do. Okay. So the point is, if you fix so if you fix the choices of scaling and you made these 2 points and they were in correspondence, right? Then you know that they both have the same scaling, and so when you do the mu thing, it's the same thing. And so the mu and the nu will correspond to each other. Okay. But it's different to rescale them so that it's q plus r and that plus that. Okay. Because once you have that, the mu's, they still correspond to each other, okay? In this way, but it might not correspond to each other in this way anymore. Okay, and you need that to correspond to each other in that way because you define the good reason to be stuck because it wasn't clear that it was true. Okay. And so we might rely on something else. So we can't just be loosey-goosey and join these 2 points and have these 2 be defined to be the points we want. We actually have to have a projectivity where the 3 points are the points that we already have and want. Okay? Yeah, my computer's gonna crash. Okay, so that's basically the start of this problem. So I'm gonna have to start a new video because my computer's gonna crash, but let's just do that. Okay, so then we actually need a projectivity that relates. So once, without changing the way that they're scaled, relates the sum of the endpoints to the sum of the endpoints with the scaling that we've already fixed for the function. Okay, so to do that, we need basically just to remember there was a lemma at the very beginning that was very helpful. It was like any 3 points are related by a projectivity. Okay, And it's so helpful that I might even decide to recall that. So it was basically like this. So let's see if we can recall that. And so if we can get any 3 points related by productivity, then we can get the 3 points we want, and then the mu's will match, and then according to the cross ratio, and then and not just match, but they'll still correspond to this this scaling. Okay, so in that way, it actually is a projective collineation. So let me just draw that. And so the thing to note is this kind of argument will only depend on basically the first two axioms. Okay, it doesn't really need anything else but incidence. So you have like, so you might want to consider what happens if the two lines are the same, because I think the argument doesn't actually work anymore. Okay, so if you have A, B, C, okay, then you have A prime, B prime, C prime, and you want some projectivities. So what you do is you label, so let's see, let's intersect these. You cross those, and you can cross those. Okay, and then you get these 2 points of intersection. You get these 2 points of intersection, and you draw a line. Okay. So what happens? What happens now? So then you label. If you can label this one A0, B0, and C0. Is that enough? So what happens is you have a perspectivity from ABC to A0, B0, C0 through A prime, yeah? And then A0, B0, C0, you have a perspectivity to A prime, B prime, C prime. A prime, B prime, C prime through A, okay? And that, if you compose them, will give you a projectivity from A, B, C to A prime, B prime, C prime. Okay, and you can do this basically with just incidence, right? You just intersect those two things to define B0, intersect those things, get C0, join the line, and define A0 to be the intersection of that line with the A line. Okay, so I think something else is required when these both lie on the same line. Okay. Okay, but I don't want to get into that at the moment. Okay, so then back to this thing, and then when we turned the page, it actually got a bit. And so the key point now we note is, so we can take this point of reference, this triangle of reference plus the unit point, to this quad. Okay, so this quad goes to that quad, and we know collineation is determined by how 4 points are acted on. So 4 points are acted on, and basically, as long as we pick P, Q, and R to be like non-degenerate, and then P plus Q plus R is something else, we can get any quad at all. Okay, so this is a generic way to define any collineation on this homogeneous real projected plane. Okay, with homogeneous coordinates. Okay. Yeah, and so then they wrote something that was confusing to us at the time. It was x1 equals p dot x prime, okay, and x2 was equal to q dot x prime, and so on. X3 is equal to r dot x prime, okay. And I guess it's a little bit confusing because we turned the page, okay. That was one thing, and then I was getting a bit tired, but actually it's the same as this, okay. So we just wrote x prime and p the other way around instead of that way around. So maybe they forgot too once they turned the page. But now it's the other way around, okay? And so if this is the x1, right, then it's gotten from x prime like this, okay? So it's actually the same thing. So this is a definition on the lines, okay? I think that would have been nicer earlier. Okay. And so that's exactly the definition on the lines. And then they introduced another notation which really threw us away. But essentially, what it means by more systematic notation is basically instead of having P, Q, and R, we just have Cij to show that all 9 things lie on a matrix as opposed to like them being in separate rows or whatever. Okay, so the whole relationship can be replaced by a matrix C equals Cij, okay, and we essentially have this x prime vector is equal to C times this x vector. Okay. And the same thing for the big x's, okay? So the big x's, so we actually also made the note that it was the columns instead of the rows, right? That's what these terms are. So the big x's actually have the same matrix, but transposed, okay? But then it's also given the other way. So you might think that the transposed, it's given for the original x into the primes, right? Whereas the other one is the primes from the original x. So in some sense it's transposed, but it's also going the wrong way. Okay, so for the big x's, you get the big x's is equal to C transpose. So if you swap the columns and the rows of the x primes, okay. So I'm using the square brackets for the homogeneous line and point notation. Okay, and then they kind of did 2 things at once, which confuses again, which is so you allow for a scalar sigma here, okay, and then you allow for a scalar rho here, okay, and if that happens, you still get the same point, right? So you can sort of take this matrix up to scalar and still get the same point because homogeneous coordinates. Okay, and then of course, if you times the 2 scalars together, they can't be 0 because neither of them is 0, right? Okay, and then the determinant of C is not 0. And that's essentially the same as saying the P, Q, and R's are not collinear. So the determinant of the PQRs are not 0 because the determinant of the C is the same as basically the PQR matrix. Okay. Okay, and then now it verifies the incidence sort of in a nice way, which I didn't get to go through. But I think we can actually replace it with the C's now. So we don't need the P's anymore, we just have the C's. Hope I don't regret erasing this. Is anyone here? I don't think anyone's here, but it's actually, I feel it's kind of more tiring to do with no audience, but because you're kind of not energized to do it, but hopefully it'll be less tiring afterwards because I didn't expend as much energy. But it is still probably tiring, I think, because I'm still trying to actually talk to someone. Yeah, so once you got these formulas, um, you can try and preserve incidence in a different way. Okay, so you have basically the dot product x dot x prime. You want to sort of say that this is equal to 0 exactly when the dot product on the other side is equal to 0. But then incidence is preserved, and they're the corresponding lines and points. And we kind of already did that before, but maybe we can have a more elegant way of doing it with this notation. So in the book it says if you take rho times this equals so by definition it equals rho times sum of x I x I. Okay. Okay, so how do we relate it to this thing? So if you have the rho x prime I, okay, that's what you have, then the sum of those things, okay, so each one of those is a row of this matrix, okay? So you have the sum, so the sum I, xi prime, and then it's row xi prime. And row xi prime is the sum of these xi's. So it's a sum across so it's the ith row, yeah. So Cij, the Ci is fixed, and the j is xj. The j changes. Okay. Then once you take the sums out, yeah. So I guess I didn't really even need to look at the book. So it's you take the sums out, and the idea is now the Cij's and the big xi primes combine in a different way. Yeah. Cij. Yeah. So if the sum is I and j now. Cij xi prime xj. Okay, and then if you look at that closely, this is the big X. The big X, so I guess it's the xi's, right? So the I, you can imagine the I moving. So let's put the J out here, the xj, little xj, and then leave the I inside. So with the I changing now with the, so a lot of the time when you do calculations, swapping the order of summation actually always gives you something interesting. Anyway, so xi prime, okay, and so now the C, how do you say this? So now the I, before it was the J that was changing, right? Now it's the I, and the I is the row. So this is the, along the column of C, right? But along the column of C is the same as along the row of the transposed C. So this is basically what I'm saying is this is the same as the first row of this. So this is actually just sigma xi, okay? Sigma times xi, okay? And so the sigma is just a scalar, it comes out. Oh, it's not xi, xj, sorry. Yeah, it's the xjth term. So we're summing up the jth row. So it gives you the capital xj term, yeah? Okay. And then you get sigma on the outside, sigma j, little xj, big xj. Okay, and that's just the inner product, little x dot big X times sigma, okay? And so if the scale is non-zero, then those two things are zero exactly when each other are zero. So that's another way to verify incidence. Okay. So I will send some extra stuff on linear algebra, but I don't expect the seniors to be able to have time to really go through linear algebra in the time that they have. But, you know, it depends on how you feel. Yeah. Okay. So that's that calculation. Now, if you want to talk about invariant points, okay, so this is where this determinant and characteristic equation stuff comes in. So you have an invariant point basically if you get the same x that you started with, yeah. So you get rho x equals cx. So if the x you end up with is the same one you started with, and so clearly this is the equation for the eigenvalue. So the rho is an eigenvalue of this matrix, and x is an eigenvector. It's not zero, okay? So then it's just a matter of solving this equation, and that exactly happens when you put it all to one side. So C minus rho times the identity matrix times x equals 0. Okay, and then for this to be non-zero, this has to be non-invertible. So that's the determinant of this is non-zero. The determinant of this is given by C11 minus, so C11 is the first entry, minus rho, C12, C13. So that's what's written in the book, okay? C22 minus rho, C33 minus rho, C23, C21, C31, C32. Okay, this is not zero determined. This is equal to 0, so it's not invertible. Okay, and so the good thing is we only consider examples Computer's still crashing. Okay, hold on. I just have to fix up my computer for a bit. Okay, so we know how to find determinants, and we're not really generally trying to solve this for anything. We kind of avoid this whole change of basis business here, actually, with just looking at some nice examples. Okay, so for example, we have that what happens if, so in this example, we have row x1 prime, so that's just equal to x1, okay? Row x2, so this is the example we have, 12.45. x2 prime is equal to x2, and row x3 prime is equal to x, so x3, but times by mu inverse. And of course, mu and mu should not be 1, otherwise it's just basically the identity, okay? Okay, so what does that mean? Remember x1 prime was a sum of all the p1, x1, p2, x2. So that's just saying that p1 is 1, p2 is 0, okay? So basically this just means that you're taking the first two parts of the triangle as the same two parts. Okay, so the only thing that changes is the R. So in terms of the matrix, what's that telling you? It's like P2 is 0, so C12 is 0. So C12 equals C13 equals 0. C21 equals C31 equals 0. And here, basically, you have, and in some sense, C11 equals 1 and C22 equals 1. And here it's the same, C32 equals C31 equals 0. C23, this should be C23. But instead of the other one being 1, it's mu inverse. So you get a matrix that looks like this. So 1 minus rho 0, 0, 0, 1 minus rho 0. And the bottom is 0, 0, mu inverse minus rho. Okay. So this is really easy to calculate the determinant of. It's a diagonal matrix. Okay. You just times the entries together. So you get 1 minus rho squared times mu inverse minus rho. Okay? Yeah. And that's what they say as well. And so you have a double root at rho equals 1, and you have rho equals mu inverse. So they're the eigenvalues. What happens? Yeah, so I mean, obviously that means the first two parts, the line that joins x1 and x2. So you have a range of invariant points, right? So these points are actually all invariant. Okay. And do you have any points that are invariant off that range? Oh, you have, I guess, this point. This point is invariant because it just gets scaled, right? So in other words, these are kind of like the eigenspaces of the matrix. But so we have to be careful with that here out of context. But and if you remember this collineation, okay, so this collineation has a whole line that's fixed, okay? So it has a whole line that is fixed, and a point that's not on the line is also fixed. So this line that's fixed is 0, 0, 1. Okay, and it has a point that's not on that line because they inner product of something to 1, right? So basically, this is the candidate for a homology where this is the axis and this is the center. Okay. So what does it say? So by 6.24 and 6.27, this is a homology with center 0, 0, 1 and 0, 0, axis 0, 0, 1. Yeah, so how do we know exactly it's a homology? What is a homology? So it was an involution. Or it was just a perspective collineation. It doesn't have to be an involution. we know something about the involution. What does 6.24 and 7 say? So 6.24 was the thing that said any collineation that has one range of invariant points, but not more than one, is a prospective collineation. Oh, so indeed. So this has a range, and if it can't have any more than one, because if it had more than one, it'd be the identity. Okay, because you'd have 4 points fixed. What does 6.27 say? For a homology, the center is the only invariant point not on the axis. Okay, so this is the only invariant point not on the axis. There can't be any other invariant points. Okay. So do we know that if you have a fixed point and a line of fixed points, that perspectivity is preserved? So okay, we know it's a perspective collineation. Do we know it's a homology? Okay, so maybe we need 6.26 as well, okay? Because that says all the invariant points of an elation lie on the axis. And so in particular, there's one that doesn't lie on the axis, so that makes that a homology. It's interesting because we haven't really checked whether it's the center or not. Yeah, so what happens if you have a fixed point outside the line? And you have two invariant lines at least. Mm-hmm. If you send another point, whose image might be here, then you join them up, and then you get an invariant line. And join another 2 points up, and wherever they intersect. So I guess to check it more explicitly, we could just have any 2 points that's not on a line, join them together, and then the point of intersection with the line would have to be the center if it wasn't a homology. So if you actually wanted to go through this, you could take some points. Let's see. It's not on that line. So something that could be a candidate would be like 1, 1, 1. Okay. Where does 1, 1, 1 go? It goes to 1, 1 U inverse. Okay. And the line that goes through both of those is, well, it could be, for example, 0, could be 1, minus 1, 0. Okay. And that line intersects the axis at maybe like 1, 1, 0, 1, 1, 0. Okay. Now let's take another point. And here we take like 1, 1, 2. And this goes to 1, 1, 2 mu inverse. I feel like I have not done anything important here. So the same line seems to go through them. How about 1, 0, 1? This will go to 1, 0 mu inverse. What line would lie on that? So something like 1, 1. It's kind of confusing. One, negative 1. Hmm. One, negative 1. That does not make any sense. 1, negative mu. It's 1, negative mu. That would make mu equal to 1. That's very confusing. Oh, okay. So maybe that's the problem. Okay, so this is going to be 0, 0, 1. Okay, that's better. Okay, so 0, 1, 0 intersects that line at 1, 0, 0. Okay, and it's not the same as 1, 1, 0. Okay, so they can't be the center. But where do these lines intersect each other? So 1 minus 1, 1 minus 1, 0, 0, 1, 0. Where do they intersect each other? Well, it seems kind of nice that they both intersect at the center, right? So that makes this a homology with this the center, and that's the axis. Yeah, so it's good, like, to check something's a collineation. A collineation is a perspectivity, perspective collineation. It's just enough to have one axis, okay? And once you have the axis, it's a homology or relation depending on whether there are any other invariant points off the axis. Okay, so that is an example of homology. So the next thing is going to be an example of an elation. Okay, elation, the happiness of doing an example. So erase this. So the other example, 12, 4, 6. Will I have enough gas to get all the way to 8.3? The row x1 prime is equal to x1 plus a1 x3. X2 plus a2 x2 x3 x3 plus, oh no, the mu is just x3. The row x3 prime is just x3. Row x2 prime is x2 plus a2 x3. Okay, so that means that P1 is 1. That's basically, this is saying this is 1, and then it's 0, A1. This is 0, 1, A2. So it might be designed to make this upper triangular, yeah? This is 0, 0, 1. Okay, then upper triangular, sorry, it's minus the row. I forgot to write minus row. So again, the determinant is just the product of the diagonal entries, because the zeros here. You can try it. You get 1 minus rho cubed equals 0. Okay, and this is supposed to end up as an elation. So that means all the rows have to be 1, okay? We're assuming A1 and A2 are not both 0. Okay, so before, like if it's 1, 1, 1, what invariant points do you have? So if there's no x3s, right, then the x1 and x2 will just be invariant. So this is an invariant range again. Okay, so that's already a perspective collineation. And the question is, does it have any other fixed points? Okay. So whether there aren't or aren't any more fixed points will depend on A1 and A2. Because if there's 0, it's like the same as before. You get the identity, right? So if you get something non-zero here, then the x1 has to be excluded. Let's see, if you wanted something invariant, right? If x1 equals x1 prime, so it's saying that it can't, there's no rows that could work, so it has to be 1. So if they're equal, then, and that's not 0, then x3 has to be 0, okay? So this is the only invariant point. So then it must be an elation, right? So elation just means there's nothing invariant off the axis. This is the axis. And the center is somewhere. I guess we can find it. So again, the axis, we know it's 0, 0, 1. So we can find the center by just intersecting some stuff. Okay. Yeah, so I guess there's lots of ways to find the center. Let's pick any point not on here. So let's say take 0, 0, 1. Okay, where does this point go? It goes to A1, A2, 1. Yeah. Then you join the line up. So what's that line? It's 0, and then it's A2 minus A1. That's the line. Okay, and where does this line intersect 0, 0, 1? Well, you can have this point 0, A1, A2. Okay, and that dot products with both of those to 0. So that's the point of intersection. That's the center. Okay. Okay, that's what the book says as well. They just did it a different way. Okay. Comparing the two parts, we see that the expression for the homology has a line-to-line transfer. Oh, it's making me think I shouldn't have erased it. Yeah, I think it's not worth writing this down. It's probably better to read that part. It's basically just rewriting this with the big X's instead of the little X's. Okay. And the fact that like they almost look the same is significant, okay? Because that's the beginning of a polarity, okay, which is going to be what's in the next section. Okay, so that finishes 12.4. All right, and so this is a good recap on what collineations are in chapter 6, if you haven't done it. And at this point, I was going to tell you some linear algebra, but we'll see. Okay, we'll see. We'll see. Okay, so I guess the point of that is, you know, some simple ways to represent all collineations of this form. So you should find if there are any relations, they should be found among them, and this happens to be one. There's a homology among them. Okay. Then you might want to say how many different ones there are and classify them and all this sort of stuff. Okay, so what am I going to do next? It's 4 o'clock. I have Okay, I'll be right back. I think I'm just gonna go to a short break. Okay, I mean this is something really cool. Okay. Okay, so let's do 8.3. And I guess if you haven't done chapter 8 for a while, we actually did 8.2 and 8.1 already. And basically, it's about conics. And what conics are is you have a polarity, and the points of the conic are the self-conjugate points of the polarity. Okay? And the lines of the conic are the self-conjugate lines. So what a self-conjugate point is so every point corresponds to a line by the polarity. Okay, so it's called the polar, and the line passes through the point itself. That's when it's self-conjugate. Okay, so the conic, sort of, and we're kind of drawing a circle because we're kind of suggestive of like ellipse. It's kind of like that conic, and we had some theorems before where it was like if you have a quad inscribed in a conic, then the diagonal triangle is self-polar. Okay, so that was pretty key. So actually, I've skipped a section on polarity, and I'm trying to sort of avoid some of the actual details here. But if you do have a self-polar triangle, what does that mean? It means that the vertices have their opposite sides as polars. Okay, and what that means is if you have a self-polar triangle and you have another polar pair off the triangle, that's four things, right? And four things determine a polarity, basically. You don't know that explicitly, but you can kind of guess. It's like a collineation, it's a correlation. And in 6.4, we know that four things determine a correlation. So actually, all you need is a self-polar triangle and one more point to get the entire polarity. Okay? So we can go into more about polar triangles. I just want to see what else is needed. Okay, so the first theorem is 8.31. It's called Seidlitz theorem. So it says, if a triangle is inscribed in a conic, any line conjugate to one side meets the other two sides in conjugate points. Let's draw this. what's that? So you have a circle. Any triangle, so any line conjugate to one side meets the other two sides in conjugate points. For some reason, I want to draw this diagram, even though it might not be the one it's referring to. It might be useful. It has a triangle inscribed in a conic. Okay. Any line conjugate to one side. Meets the other two sides in conjugate points. So any line conjugate to one side. Okay, maybe this is a good diagram after all. So that's obviously the triangle. Okay, so you have a triangle inscribed in conic. Okay, then any line, maybe this will be the line, right? This is PQR. Okay. And then any line L, which is conjugate to one of the sides. Okay. Conjugate to a side meets the other sides at conjugate points. Okay. So what does that mean? Where will my pens go? And so this is like a side, okay? If you're the tangents at P and Q, okay. So remember that the polar of big D, so the points where the tangents intersect, the polar is the secant going through the tangent, okay? And, well, so any line L has to pass through this big D, okay? So this line which passes through the pole of little d is by definition a line conjugate to little d. So L and D are conjugate. Okay? And what we want to show is that the other two sides, so these 2 points are conjugate. So this point and this point are conjugate. Okay? I don't know why I'm going by the book. I can basically see what's going on. Okay, so what does it mean for the points to be conjugate? It means the polar of this point passes through the other point. Okay. So what you could do is, so this is where knowing the previous theorem helps, okay? So basically one way of doing this is, so the most natural situation for conjugate, well, the one we saw first for conjugate points was when you have a self-polar triangle, right? Because this is the vertex, its opposite sides goes through the other 2 vertices, yeah? So if you can realize these 2 points as the vertices of a self-polar triangle, then naturally Um, Actually, the polar of this will go through that. Okay. And so we have 3 points in a conic. We just need a fourth now, because we know if we have a fourth, the diagonal triangle is self-polar, right? So see, what we have to do now is pick another point on this. So PQRS. So maybe it's suggestive picking it there. Okay. Where would you pick it? Can you pick an S that intersects both of them? So, for example, you could pick. Where could you pick it? You just draw a random line. But to be a diagonal point, it would have to intersect Q. It would be like this. And this would be our S. And then the claim would be that then PS, this point is collinear. And then you get a self-polar triangle. Okay. Yeah, I mean, that's what the proof says as well. It's just referring to another diagram. I just don't understand what the notation is. RC meets the conic again in S. What's R? What's C? Hmm. No, so I guess in this case, this would be C. If RC meets the conic again at S, let's have a look. I need another pen. This would be S. Any line conjugate to PC is the polar of some point C on PQ. Hmm. Oh, I see. So I guess what that means. So one thing we can deduce is since little l passes big D, then big L must lie on little d. But where does it lie on little d? Okay, so if you put S here, and you join, stop crashing. Mm-hmm. Mm-hmm. Hmm. So what does it mean by these lines are all concurrent? Okay, maybe we have to use. Okay, so describe a triangle. Any line C conjugate to PQ is the polar of some point C on PQ. Yeah, so capital L lies on PQ, sure. Okay. Then RC meet the conic again at S. So maybe it shouldn't be here. Let's try it again. Then RC, so it's on PQ somewhere. Maybe it's here. And RC meets the conic again at S. Okay. Okay. So the diagonal points of PQRS are self-polar. Triangle. Oh, and is C one of the sides? You need C to be one of the sides. From a self-polar triangle whose side C contains the conjugate points A and B. One on QR and the other on RP. One on QR and the other on RP, huh? Hmm. Okay, so I guess it's clear that this capital L is a diagonal point. No, so if C is a diagonal point, oh, I think I get it now. Okay. So if L, okay, so basically you have the diagram of the triangle. You have some line passing through big D, okay, and the pole of that line has to lie on little d, okay, by the incidence preserving. And so that's big L, okay. So if you put L here and join it to R, it'll make some S, and that'll be PQRS as a quad, okay, and then L will be a diagonal point, okay. And so we know that. Okay, so we know that the diagonal points form a self-polar triangle, right? So in particular, the polar of L is little l, okay, is the opposite side of that vertex on the triangle. Okay. So the other two diagonal points must actually lie on this line. Okay. I mean, it doesn't seem obvious from the way it's drawn, I guess. But so ignore this part. But if you want to find another diagonal point, for example, well, it's not going to be this one. Yeah, I guess maybe the point is L shouldn't be there. It's not so. Yeah, so most likely, so we don't actually know the position of L, okay? But it should actually most likely be where we said it was. This should be S. And then R, S. So this should be L. Okay? Basically, the point is the opposite sides of L is the polar of L in the self-polar triangle. And so therefore the vertices of the self-polar triangle have to be conjugate. So the vertices is exactly where the sides of this triangle meet here. Okay? Okay, so that's sorted. 8.31. Okay. So now it says, now we are ready for one of the most significant properties of a conic. Okay. So that's what we're up to right now. Okay, so we're up to the most significant properties of a conic. Okay. So assuming we know Seidel-Wich's theorem, when you have an inscribed triangle, any line going through the pole of a side, okay, meets the other two sides in conjugate points. Okay, so that was a nice theorem, but the book says that after, so this, I don't know, it's like a little bit of a punch in the face to Seidel-Wich, but we have Steiner's theorem. Said to be one of the most significant properties of a conic. Okay, and I guess my question to you, which I wrote in the email, is what is so significant about it? What is so interesting about it? Okay, and it's something you'll actually agree it's interesting. So the theorem states: let x and y be lines. Basically, in this diagram, it's going to be x and y. Okay, they're lines through fixed points of a conic, variable lines. So the notation may be a little bit misleading. There could be more than one line. Okay, it's only one line drawn. Variable lines meeting on the conic. So at R, yeah? And then they pass through two fixed points. So this is P and Q, okay? And it's a very simple conclusion. So these lines are perspective to each other. There's a perspectivity that relates them. Okay. Okay, so what does this theorem try to say? Okay, maybe we can just prove it by thinking of how the other theorem works. We have two lines meeting, and we're looking for a projectivity that relates them. Okay, so if we have a line with a pair of conjugate points, is that an involution? What do we have? So the tangents of P and Q meet in the point D, you know? D is the pole of PQ. C is a fixed line through D, so this is a little L for us. And does not go through P or Q. Okay, so I mean, Seidowitz contributed to this theorem, I guess, because it's being cited. Meeting X in B. Yeah, so this is called B, and this is called A. Okay, RQ. This is called C1. Yeah, so I guess it said what I was saying. So B and A, okay, being conjugate points on this line, induce an involution, I think. So using Seidewitz's theorem, B and A are conjugate. And so it's a pair of the involution of conjugate points on C. So if you remember, a polarity induces an involution of conjugate points on a line, yeah? And the involution just basically pairs up conjugate points, okay? And basically, because B and A pair up, any pair of an involution determines does it determine the involution? Maybe not. The point is there is an involution that is determined by this conjugacy thing. And so B and A are projectively related to each other, okay? So if B and A are projectively related to each other by means of involution, then how can we extend to that a relation between X and Y? So X is a line passing through B. Y is a line passing through A. Through and R. So it's kind of like this. So BA is projected, it's related by an elementary correspondence to XY, yeah? Through R. You can think of it through R. But BA are involved in an involution with each other. So you can think of that as AB, right? But then AB is related to through R to YX. So you have a productivity that takes YX to XY. It's actually an involution that takes X and Y to each other. Okay, so the way they wrote it was yeah, so I guess you need R to be on the conic for it to work, because you need the previous theorem. So they wrote this x, b, yeah. So there could be a lot of b's and a lot of x's going through P, yeah? And then that's related to A, because it's an involution, and then A is related to Y, okay? Yeah, which is basically the same as what I said. The following remarks make it natural for us to include the tangents at P and Q, okay? So notice that the idea of continuity, though intuitively helpful, is not assumed. Writing little d equals PQ, C1 as that. Consider the possibility of using capital P or capital Q as a position for R. Okay. So what happens if we move R all the way over here? So then Y becomes D, yeah? Then Y becomes, so if R equals P, then little y equals D, and little x becomes the tangent of P. Okay, little x becomes little p. And so big D just becomes A, yeah? D becomes A, and C1 becomes B. And what's the claim? What's the conclusion? That the tangent of P is related to D? Let's see here. Yeah, so we fire alarm. I have to stop this.